Hey guys, today we're going to test our knowledge with gas laws, understanding Boyles, Charles, and hopefully we can get to some other gas laws. So let's go ahead and get started. First question deals with Boyle's law, and whenever we're trying to answer these Boyle's law questions or any gas law question, we need to one understand the formula involved, and we also need to understand pressure conversions because they're an invaluable tool. One other standard of reference I would include, just because I tend to care about it, is you want to make sure that you're aware of the conversion between milliliters to liters. If you're ever put in a situation where it gives it to you in milliliters, and sometimes that will occur, you want to know that 1,000 milliliters is indeed equal to 1 liter. So for Boyle's law, the unique thing about it is, in general, as long as your pressure units and your volume units are consistent, you can answer the questions as is. Although, as a standard of preference, I tend to lean towards putting my units of pressure in ATMs, and I tend to put my unit of volume in liters. Now, for Boyle's law, you need to understand that it expresses an inverse relationship. And what that inverse relationship means is that as the pressure increases from P1 to P2, the volume will decrease. So that's what an inverse, or I guess I would call it indirect. It depends on how you look at it. When I talk about relationships, it's more of an inverse. One goes up, the other goes down. So when you're looking at that graph, you want to make sure you can explore that relationship when you are comparing P to V, where if the pressure is going down, this volume is going to increase. So make sure you understand that. Alright, so let's get started. We start with, if 22.5 liters of nitrogen at 748 millimeters mercury are compressed to 725 millimeters mercury at constant temperature, what is the new volume? Now remember, constant temperature is definitely a giveaway or a telltale when you're dealing with Boyle's law, because usually you're comparing pressure and volume solely if you have constant temperature. Sometimes questions might trick you and say that, it gives you a certain temperature and it doesn't give you another temperature listing. You could assume that that temperature maintains the status quo. So we can assume here that we have 22.5 liters, and that can constitute our V1. And we know that 748 millimeters of mercury is a pressure measurement, and we can assume that to be our P1. Now our P2 in this question is actually given, and that is 725, and we are questioning or trying to determine the value of V2. Now, as I mentioned, when dealing with Boyle's law based questions, it doesn't matter if the units are in ATM, millimeters of mercury, or anything thereof. However, as a standard of preference, I tend to lean towards putting my units in ATMs. And to achieve that, especially going from millimeters of mercury to any unit, you just divide simply by 760, as 760 millimeters of mercury is equal to 1 ATM. So, setting this up, initially, I say 748 millimeters of mercury times the V1, which in this case is 22.5 liters, is equal to my P2, which is 725 millimeters of mercury, and my V2, which is my unknown. I'm then going to proceed to divide each of those by 760, the pressure units, because that's going to convert these guys to ATMs. So dividing those converts those to ATMs. And when I divide 740 by 760, I'm sorry, I get roughly 0.984. So, .984, my unit is ATM. I'm still going to end up multiplying that by the 22.5 liters. And I'm going to go ahead and proceed to divide this 725 to convert that to ATMs. Divide that by 760. That yields 0.954 ATMs. And my V2 is still unknown. Now, I'm then going to proceed to divide both sides by the 0.954 here. And that's going to eliminate this pressure being on the right-hand side of the equation. And I'm going to divide that on this side because you want to kind of apply kind of an identity function here. Alright, so those check out. That leaves me with V2. And V2 is going to be equal to whatever the product is of this equation. In which, to solve it, I just simply take 0.984, multiply that by 22.5, and I'm going to divide that by 0.954. And that's going to give me approximately 23.2. And that's going to be in liters. Now, what should be noticed is if you compare the values of P1 to P2 and V1 to V2. P1 has a value of 748, and that value decreases to 725. And because there's an indirect relationship, this is going to imply that going from V1, which is 22.5, we should expect this value of V2 to increase. That value does increase. We didn't know prior to actually solving the problem by how much it increases, but we should know that because of the inverse relationship, this number does increase. Okay, so let's look at another one. Let's go ahead and look at number 2 here. I'm going to fold my paper to make some room. Oh, folding it too much there. Alright, so for question number 2, we're still dealing with Boyle's law, and this question states a gas with a volume of 4 liters at a pressure of 205 kilopascals is allowed to expand to a volume of 12 liters. What is the pressure in the container if the temperature remains constant? Remember, temperature remains constant, or they don't give you another value and they're not asking you to solve for it, then you're dealing with this pressure and volume based question, which is going to likely imply a Boyle's law like problem. So we don't have our conversion like we generally did before up there up top, but I can tell you that the conversion unit for kPAs is going to be 101.3, and we're going to use that to convert this guy to ATMs, and then we can go about solving it as we've done before. So let's go ahead and get ready to look at that. And to do that, we're going to assume that our P1 value in this case is 205 kPa. Our V1 is 4 liters. We don't have our P2 value. And then our V2 value is actually 12 liters. Now, as I highlighted before in question number 1, there is an inverse relationship. This is going to imply that comparing V1 to V2, we notice an increase in the volume in liters. This is going to imply that the P2 value is in fact going to decrease. Now, to solve this question, all we're going to do is we're going to simply plug in the values. That's our P1. 4 liters is our V1. Our P2 remains unknown at the moment, and our V2 is 12 liters. So then we're going to go ahead and solve. We can actually keep this guy in kPa because the answer we're going to get is going to be in kPa. If we wanted to, we could actually convert this to ATMs. For consistency's sake, I can go ahead and express how that would look in ATMs. 101.3 kPa is what you divide that by to convert it to ATMs. That yields 2.02 ATMs. And then we are going to multiply that times our 4 liters, and everything else checks out as the same. P2, we don't know, 12 liters. I'm trying to solve for. Divide both sides by 12 liters. That cancels out. And when we step forward in solving it, we yield a value of 0.673 ATMs is equal to P2. Now, if we wanted to solve this using KPA, we would also be able to obtain the answer. We wouldn't necessarily have to divide by this value. Simply put, 205 times 4 divided by the 12. It's going to give us a value of 68.3 kPa. And that is very similar. In fact, if you wanted to compare that, you would simply just divide this value by 101.3 to get what the conversion is in ATMs. So either of these would be fine, depending on what the question was asking for. If it wanted the pressure in kPa, you could express it using that. If you wanted an ATM, you can express it using that. They're very similar. So that completes our instructions on Boyle's law. I'd like to get ready to proceed to our next part, which is going to definitely deal with Charles' law. Let's take a look at some problems that feature Charles' law. So we have our Charles' law equation indicated here. And the interesting thing about Charles' law, which is different from that of Boyle's law, is that it compares volume and temperature. It has a direct relationship, which means that as the volume increases, so does the temperature. And so what's also important to note is that I usually use units of liters for my volume. And for temperature, you absolutely must use Kelvin temperature to get the correct answer. So let's get started. In this first question, we're asked to calculate the decrease in temperature when 6 liters at 20 degrees Celsius is compressed to 4 liters. So first we're going to solve for one of our variables and then answer the question by calculating the amount of decrease. So let's go ahead and look at doing that, shall we? We have our volume, which our V1 in this case would be 6 liters. We also have our T1, which is going to be 20 degrees Celsius. That's going to later be converted to Kelvin temperature. We now have our V2, which in this case is 4 liters. And we are trying to extract the value of T2. Now, if you notice anything, that T2 is located in the denominator position, and we are going to have to solve for that. However, what I tend to recommend is to position the variables such that all of those variables are located in the numerator position as opposed to some of them being located in the denominator position. So rearrangement would lead to this equation. V1 T2 is equal to the product of V2 T1. And then you can cross multiply or divide or whatever you see fit going from there. Now, I'm going to go ahead and go forward with converting this T1 value to Kelvin. That can be achieved by adding 273 roughly to equate to 290 Kelvin. So I have that value. I'm going to go ahead and plug in my V1, in this case 6 liters. Going to multiply that by my T2, which is unknown at the current moment, and set that equal to the product of 4 liters and 293 Kelvin. So from there, divide both sides by 6 liters. And solve. This is canceled out. So our product is going to be equal to T2, of course. Using our trusty calculator, we take 4, multiply that by 293, and we divide that by 6. That gives us a value of 195.3. However, if we're using 3 sig figs, I would go ahead and round that to 195 Kelvin. Now, that's not the answer to the question. That's just the answer to T2. And if you recall, it's saying calculate the decrease, which is basically the change in temperature from T1 to T2. Now, if you used and kept the values in Celsius, I could imagine that you would have gotten a kind of completely different answer. So we're going to, in this case, just subtract T1, which is 293, from our T2, which in this case is 195. And that will give us our delta T value, which is what they're trying to find. Delta meaning change, and T, change in temperature. So 293 minus 195 yields 98. So that is the decrease in temperature that is experienced. Remember, that's not the same thing as T2. T2 was this value. The answer that we're looking for is this one. All right, let's go ahead and move to our next question. I'm going to fold the paper a little bit here to make space for myself. And once again, I'm folding incorrectly, but we'll go ahead and make do. All right, so in this next question, we're looking at a gas that occupies 900 milliliters at a temperature of 27 degrees Celsius. What is the volume at 132 degrees Celsius? Now, it is very tempting to attempt to solve these problems using the temperatures in degrees Celsius. However, they must be solved using Kelvin, or you'll end up with perhaps an incorrect answer. Most likely an incorrect answer. So let's look at this. I'm going to go ahead and write down V1, T1, V2, T2 as my variables given. I also want to list the ones that we have. And we're giving a volume of 900 milliliters, which I'll later convert to liters. We have our T1 value, which is 27 degrees Celsius, which I'm going to convert that to Kelvin. Our V2 is unknown, and our temperature, or T2 rather, is 132. And I want to take the time to point out a couple of things before we go forward for solving the problems. Before you go through anything, because volume and temperature share a direct relationship as it relates to Charles' law, you should see an increase in this V2 value, and I'll explain it. According to the law, it states that as this guy increases, which is 27 going to 132 degrees Celsius, we can surmise that V1 should increase from 900 milliliters to some value. So when we solve it, we're going to look at that relationship and see if that holds true as well. So let's go ahead and solve it. I'm going to convert this guy to liters. And you can convert to liters by dividing milliliters by 1,000. I'm going to next convert from 27 degrees Celsius to Kelvin, which will yield roughly let me correct myself, 300 Kelvin. I still don't know my V2 value, but that's going to be in liters, whatever it is. And we're going to add 273 to this 132 to yield a value of, bear with me, 405 Kelvin. So now let's go ahead and plug these in and solve for V2, shall we? V1, actually let's back up. Let's recall that V1 T2 is equal to V2 T1. And so let's go ahead and solve this correctly. We'll go ahead and place our value of V1 in place. Then we'll go forth and calculate T2, which is 405 in this case. Then we'll go ahead and connect that to this V2 that we are not sure yet of, and we'll plug in our T1 value here. Divide both sides by 300K. And then use our trusty calculator to solve. 0.900 times 405 divided by 300 yields a value of 1.22, and that is in liters. Now, as we stated earlier, this should also increase according to the direct relationship shared in Charles' law, which states that as volume increases, temperature shares a direct relationship, which means it consequently increases. This temperature increased from 300 Kelvin to 405. This increased from 0.900 liters to 1.22 liters. And there you see how the comparison of Charles' law does in fact hold up when comparing the two. Now, if you look back when we were comparing them, we had 6 liters here. This decreased to 4 liters. That should have said that our 293 Kelvin of T1 should have decreased to a much lower value, which indeed did hold true, and it decreased to 195. And so even if you're not sure of your answer when solving a Charles law based question, it helps to understand the relationship of volume and temperature being direct so that you can effectively solve them, and fact check yourself and make sure you are on the right track when solving these type of problems. So that should conclude our information on Charles' law. Alright, so let's look at some of the features that make the combined gas law unique. The combined gas law actually combines pressure, volume, and temperature all into one large equation. And it's very important that as we go through solving this, we understand that pressure must be in ATMs, volume should be in liters, and temperature must be in Kelvin. And so let's explore trying to solve this using that approach and understanding. So, a small research submarine with a volume of 1.2 times 10 to the 5 liters has an internal pressure of 1 atms and an internal temperature of 15 degrees Celsius. If the submarine descends to a depth where the pressure is 150 atms and the temperature is 3 degrees Celsius, what will the volume of the gas inside be if the hull of the submarine breaks? So, even without decoding what this question is saying, I do see that there are 5 numbers given, which means that I'm trying to find that 6th variable. To solve for that 6th variable, we'll need to calculate using the 5 variables provided being sure to make sure that they are in the appropriate unit format. Now, to simplify, I tend to put my variables found in the denominator in the numerator. So let me go about rearranging that equation to represent that. Rewritten, the product of P1 V1 T2 is equal to P2 V2 T1. And so essentially from there I'm going to attempt solving the problems, being sure to make sure that my units are consistent. Now, looking at them, they are in ATMs. The pressure is in ATMs because I have two pressure conversions here and here. I'll represent that as P1 there and P2 respectively. P1 will be 1 ATM. P2 will be 150 ATMs. Next, I'm going to look at my T1 and T2. My T1 and T2 are equal to 15 degrees and 3 degrees Celsius respectively, which I'll go ahead and convert those to Kelvin. By adding 273 to each of them, which roughly ends up yielding 288 K, which is Kelvin, and 276 K, which is Kelvin. Alright, we have our V1 and V2 next, and one of these V's we're trying to determine. I'm going to assume in this case that we are solving for V2. So we'll put a question mark at V2, and V1 is represented by the 1.2 times 10 to the 5 liters. And we'll put that here. Alright, now I'm just going to plug away and try solving the problem using kind of algebra and multiplication and that kind of stuff. So let's go ahead and proceed. P1, 1 ATM, multiplied by V1, which is the 1.2 times 10 to the 5th liters. That's going to be multiplied by my T2, which in this case is 276 Kelvin. And I'm going to set that equal to the product of 150 ATMs, which is my P2. My V2 I'm not sure of because I'm solving for that. And my T1, which in this case is 288 Kelvin. And I will need a calculator to solve a question such as these. If I'm multiplying 1 times 276, it's going to be its own product. And I'm going to next multiply that by 1.2 raised to the 5th power, well, times 10 raised to the 5th power. And that will yield a large number, which can then be compared to the numbers on the other side. $150 ATMs, V2, 288 Kelvin. Now, technically, if I was dealing with units, this would be ATMs times liters times Kelvin. It'll be simplified once we actually find our products. I'm going to go ahead and next multiply 150 by 288. It's going to yield this number. Now, you can round. There's no harm in rounding in this case, as long as you round to the correct number of significant figures. In each case, I believe for the left side, number 6 would have been 2 significant figures. On the right-hand side, it would have been 3 significant figures. So I'm going to next divide both sides by this number, this much larger number. And that will give me my value of V2 in liters. So Here 3, 1, 2, 1, 2, 3, 4, divided by 4, 3, 2, 0, 0. And that's going to give me a value of 766.7, which I definitely am going to round that. Seeing as though this 1.0 ATM has the least amount of sig figs, I'm going to assume, well, actually the 3 degrees could be regarded as having one significant figure. So if we really were rounding it, a raw answer would be closer to 800 if you wanted one significant figure for liters. Or alternatively, you could use 2 sig figs, and if you wanted 2 sig figs, it would be 770 liters. I'm going to lean towards the 1 sig fig, and that's going to be my answer of 800 liters because I want 1 sig fig.